Okay, now that you know how to do a one sample test where we're comparing a sample to a population, let's talk about what happens when we want to compare two samples. I've kind of made up some numbers over here, and what I'm pretending is that we took two samples of children in New York and in Dallas and asked them to rate Dr. Pepper on a scale from 1 to 10. You probably know it's a lot more common in the South, so I've just made it up to kind of reflect that. So we're going to pretend that we asked them first as children and then as adults. So there's two different rankings, and maybe the first one, they were 10 and the next one they were 20. There are two different ways to make this comparison now. I can compare people in New York to people in Dallas, which was probably the initial purpose. But then I can also compare children with themselves as adults. So I'm assuming here that I've ordered these in the same way. So this person who ranked Dr. Pepper an 8 as a child has ranked it now as 10 as an adult. So these are same person next to each other, and so are these. I could compare just New York children to Dallas children. I could compare all the New York answers to all the Dallas answers. That does, of course, skew some things because it makes everyone worth two people, but at separate times, so it's not a super valid thing to do. You really should do children to children or adults to adults or person to themselves. They're both called two-sample tests. If I compare the New York children to the Dallas children, I am doing an independent or unpaired test because those New York children have nothing to do with the Dallas children other than their children. So they're not paired, the samples are independent of each other. If you didn't like my New York sample, you could go take another one and we could still do the test with my same Dallas ones because they have no effect on each other. So that's one way. For me, I can put it, because I'm on the computer here, I can copy this into my calculator. You would have to type it in, but you can. So you can pause this right now and go ahead and type it in if you want. You need a spreadsheet as always, and we should put this in a list. I'm going to name this NY Children, and then I'm going to name this one Dallas or DFW Children. And so I'm going to take the New York children, copy this in, and these, and copy this in. I'm comparing then two samples, and in both cases I'm looking at the mean. So the way I run the test is I go Menu, Statistics, Tests, probably no surprises there, to sample, and then I've got Z versus T. My samples are small, so I'm going to choose T. It actually never will hurt you to choose T because with T it depends on the sample size. As the sample size gets larger, it starts to be exactly like a Z test. But this one we definitely need a T test. Then I'm asked, do you have the data or the stats? Because I gave it a list, I have the data. Stats would mean I'm going to tell you the mean and the standard deviation for each group. And while I could go calculate that, I might as well just give it the list and let it calculate it. A is the first list, B is the second list. And what I believe is that New York children would like the Dr. Pepper less than Dallas children, and New York children was my first list, so I think the first list is going to be less because it was a ranking from 1 to 10. I think they'll rank it lower. Okay, so over here I've got a t-value of negative 2.78. The p-value is 0.003931. Pretty much any level of significance you would choose in normal practice, this would be lower than alpha. So definitely we have shown that the New York children do not like Dr. Pepper as much as the Dallas children do. The next thing though that I might want to do is compare those Dallas children to themselves. I did not mean to delete that. And so I'm going to put here DFW adults. Strange things are afoot on my computer. Let's see if these are okay. Okay, so somehow I had gotten off track, but I think I'm okay now. Okay, so now I want to compare these two to themselves. But I no longer just care about the average of the sample. I actually care about the change in individual people. And this could have been not just a person compared with themselves, it could have been a child and their sibling. Or the adults, it could have been the person and their spouse, because those would affect the comparison. If one person loves Dr. Pepper and they're married to someone else, that person probably ends up drinking Dr. Pepper. Not necessarily, but maybe. And children who are siblings are likely to have been offered the same things, and they've grown up on the same things. So those are also paired. Essentially, if there's a way that given the two lists, you and I would pair them in the same way, if we were given one list and then a list of their siblings, I would pair the siblings together, and so would you. It's the natural thing to do. If there's a natural pairing, it's called a dependent two-sample test, or paired. If it's paired, then what you actually care about is the difference between two on the same level. So in this case, I care about the child and themselves as an adult. What happened there? This one went up 2. I care about the fact that that went up 2 rather than what happened to the average. So we look at them in the paired way. If you were looking at siblings, you'd want to know the difference between siblings, not the difference between the first set of siblings and the second set of siblings. Especially with siblings, there would be no reason to believe that the average of one would be different from the average of the other, but perhaps the difference between siblings is significant. So I'm rambling a little, but here's the point. What we care about is this difference. If it's paired, it becomes a one-sample test, and you just find the difference. So equals C minus B. And now we have this one went up 2, this one went up 2, this one didn't change, this one went up 1, this one went up 2, up 1, up 1. That one went down 2, this one didn't change at all, and so forth. So we're looking at what's happening overall to individual people. Now that we have this, I'm just going to run a one-sample test. So it's a two-sample test, but it's paired, so the test that I run after I've turned it into a one-sample test is a one-sample test. So I go to one-sample t-test on data, and my list is D. I expect there to be no change, because that's the null hypothesis. Maybe you expect something different, but the null hypothesis is that they're the same. So mu should be 0, because if the two things are the same, then when you subtract them, you get 0. We didn't check. It kind of looks like they went up, but we'll just stick with the alternative of it's changed. We just want to know, is it different from 0? And we get a t-value of 2.9 and a p-value of 0.008. Which is very low, so definitely there was a change, and I believe it went up, but you could check that. It looks kind of like only maybe 3 people went down, so I think that it was an increase. People liked Dr. Pepper better over time. Probably not true, but I made the numbers up. But that's what the conclusion would be. So the difference between paired and unpaired, first of all, is that unpaired it's called independent as well, and there's no natural mapping person to person between the two. And then paired there is, and then also unpaired there's no way to turn it into a one sample test because you're comparing whole group to whole group. So it's called a two sample test even on the calculator, and the other one, when it's paired, is a two sample test which turns into a one sample test after you compare each individual pair to itself.